Hey everybody! In this video, I'm going to show you how to derive temperature from the thermal band of a satellite image. In the previous video, we gave an overview of thermal remote sensing and talked about how estimating the temperature of water on Earth's surface is actually one of the most robust things you can do with satellite imagery. So here's an example, two temperature maps of Lake Tahoe, California, inferred from the MODIS sensor on board the Terra satellite. So I know what you're thinking, we're going to derive some equations. I feel the same way, but we'll get through it. If you're in my class, you don't need to memorize or derive these equations yourself, but you will be responsible for applying them in lab, so you may want to pay attention, take some notes. So we'll start by going over the concept of emissivity, then we'll look at how to compute object temperature. Actually, we're not going to do part 4. So remote sensing can measure radiant temperature using a thermal band, and radiant temperature is the temperature inferred from the radiant output of the object. That's slightly different than the kinetic temperature, which is the actual temperature of the object. And these two things are related by the emissivity. The emissivity is the ratio of the emitted radiance divided by what would have been the emitted radiance of a black body at the same temperature. Okay, so if something's a perfect emitter, it's going to emit the denominator, but most things on Earth, including water, do not emit as much as a black body. So the emissivity becomes a fraction between 0 and 1. And of course, a black body itself would be 1. So mathematically, that just works out to the radiant temperature is equal to the kinetic temperature scaled down by the emissivity. Now it's important to remember that emissivity is wavelength specific, okay? So for gray bodies like water, emissivity is always the same fraction. It's always 0.95 at any wavelength. But for many surface materials that are selective radiators, like rocks, the emissivity may change quite a bit as a function of wavelength. So it's often the case that we actually don't know the emissivity of a surface on the ground unless it's water. Okay, so how are we going to get temperature? We'll begin by recognizing that emissivity is actually related to reflectivity. And here's how we can do that. We'll first set up a budget of radiation. So that's going to say that the incident energy is equal to whatever gets absorbed plus whatever gets reflected. Okay, so it's a budget. Whatever comes and hits the ground only has two things it can do: be absorbed or be reflected. Okay, right there. Okay, so there's our budget we just established. Now if we just divide all the terms by incident energy, by the same denominator, we'll make them into fractions, and we can then set them equal to 1. And then what we can recognize is that actually these are familiar terms. Right here, the fraction of reflected energy over incident energy. That is the reflectivity, right? Okay. The fraction of absorbed energy over incident energy. That is the absorptivity. So we actually already had this equation. Reflectivity plus absorptivity equals 1. And again, this is just another way of saying it's a zero-sum game. Energy either has to be reflected or absorbed, and that those two fractions have to add up to 1. In this case, the wavelength subscript here is just denoting we may be considering reflectivity or absorptivity over a narrow range of wavelengths. So we might refer to that as spectral reflectivity or spectral absorptivity. Or we could be considering it over the entire electromagnetic spectrum. But usually we're talking about just some specific subset in the far infrared. Okay, so for the next step, we're going to make a small assumption that if the surface we're looking at is in thermal equilibrium, all absorbed radiation must ultimately be re-emitted, right? If the sun is shining on a rock and the rock is not changing temperature, right, we know that energy is still being absorbed And by definition, if it's not changing temperature, the same amount of energy must be being emitted as well. Otherwise, the temperature would be getting hotter or colder. Okay, so thermal equilibrium means emissivity must be equaling absorptivity. So then we'll go back to this equation we just derived, and we'll just plug in emissivity for absorptivity here, right? So we got rid of the absorptivity. So now we're saying there's a balance between reflectivity plus emissivity must equal 1, okay? And if another way to say this is whatever energy isn't reflected immediately must eventually be re-emitted. If it goes into the rock, it's got to come out. Okay, so having derived that equation, and that's going to come back to us, now we can go ahead and I'll show you how to actually compute object temperature. And we're going to do this in 3 steps. First, we're going to convert digital numbers to measured radiance, okay? So digital numbers are how the information is encoded in the file, and radiance is what was actually measured at the satellite. Then we're going to convert that measured radiance to a black body radiance, and then we're going to convert that black body radiance to a kinetic temperature. So in this step, number 2 in particular, we're going to be using the emissivity to essentially convert the measured radiance to what it would have been if it was a black body emitter. All right, so actually step 1, we're actually going to skip because you know how to do this. We've covered it in a couple previous videos, and the links to those are here. Please check them out. So assuming you've now converted to units of radiance, the next thing we're going to do is set up another budget for measured radiance, okay? So if we call measured radiance at the satellite sensor L tote, okay, those photons, or that energy, are coming from 3 different places. Some of them are emitted from Earth's surface. Some are reflected off of Earth's surface. And then some of them come from path radiance. Path radiance is photons that either were reflected off the atmosphere, or in the case of thermal remote sensing, these are photons that actually are emitted from the atmosphere, that might be emitted from clouds, because all warm matter emits radiation, including gases in our atmosphere. And those actually become significant in thermal remote sensing. Okay, so we got emitted, reflected, and path radiance. And then we can further break those down. Emitted is equal to the black body radiance, okay, so whatever that let's say it's a rock, whatever the radiance emitted from the rock would have been, times the emissivity, okay, adjusting it down for the emissivity, so that, and then times the transmissivity. This transmissivity T is a unitless fraction denoting what fraction of the energy successfully passes through the atmosphere. So it's between 0 and 1. A transmissivity of 0.9 would suggest 90% of the emitted radiation from the surface actually makes it up to the satellite sensor. Okay, reflected is very similar. Reflected, we're going to start with downwelling radiation. So this could either be coming from the sun, or it could just be radiation that's actually downwelling from a cloud or from the atmosphere. We're going to adjust that by the reflectivity, because only some fraction of it's going to get reflected. And then we're going to further adjust it by the transmissivity again, the exact same value we used before. And then finally we have this term, the upwelling radiation, or the path radiance. And usually in remote sensing, we're going to look this up or compute it in a computer model, an atmospheric model. This is something we really have no way to know other than by looking it up from an atmospheric model, or if we have another sensor of some kind. Okay, congratulations. That was the worst of it. So now let's just do some solving. So we've set up our budget, okay? Now keep in mind, this is what we just set up on the previous slide. Keep in mind, L tote is what we measured, and L black body is what we're trying to get, okay? That's what we're solving for. So we're going to do a little algebra and solve it for black body radiance. But now we've got all these terms, and we need to get rid of some of these terms. In particular, we want to get rid of the reflectivity. And we're going to actually now use the equation we derived in the first part of this lecture to swap out reflectivity for 1 minus emissivity, using that unit sum we developed earlier. All right, so we've gotten rid of reflectivity down to here. Now that we've done that, we're actually ready to solve. So now we're just going to plug in known quantities, and we know all these things. L tot was measured. That's what we were given, that's what we started with in the satellite image. Transmissivity we'll often look up from an atmospheric model. Emissivity, if it's water, we know that's 0.95. If it's some other material, we do need to either assume it or actually find a clever way to estimate it. And there's different ways to do that. And then downwelling radiation and upwelling radiation, again, we would look up in an atmospheric model. But we know all those things, and now we can solve for black body radiance. So finally, step 3, we're going to convert that black body radiance into a temperature, okay? What we've done up until now, we've essentially estimated how much radiant excidence or radiant energy is coming from this surface. We adjusted it by emissivity so that now we're saying kind of how much would be coming from it if it was a black body. That's what LBB is. So now we can go right to Planck's law, which only applies to black bodies, importantly, right? So Planck's law assumes you're talking about a black body. And we can solve for temperature, solve for kinetic temperature here, okay? And turns out we do know most of the things in this equation as well. We know wavelength, we know Planck's constant, speed of light, the Boltzmann constant down here. Nonetheless, it is a bit of a bear, and actually for most satellites that have thermal sensors actually have some simplified version of Planck's equation that you can use to get temperature. So for example, if you're working with Landsat thematic mapper or enhanced thematic mapper, you can use this equation where K1 and K2 are constants that incorporate all those things. Planck's constant, Boltzmann constant, speed of light, wavelength. And they're basically tuned up with the exact wavelength interval for the thermal bands of thematic mapper and enhanced thematic mapper. So if you're using those, you can actually just plug right into this equation. So in summary, we used 3 steps to compute temperature. We converted digital numbers to radiance. We then converted that measured radiance into a black body radiance. And then we converted that black body radiance to temperature using Planck's law in the last step. Thanks a lot for listening.